Okay, now that we've covered the well equations for confined aquifers, let's go ahead and look at unconfined aquifers. In my experience, it's more common that we're dealing with unconfined aquifers. So these equations are the ones that we're most likely to use, especially when we're doing designing construction dewatering systems, which will be our next topic. And so in this case, with an unconfined aquifer, this is our free surface. It's just the top of the saturated material. There's no confining zone. It's all a single zone. This dashed line, once again, is our initial water level elevation. And with a confined aquifer, we had purely horizontal flow to the aquifer in a radial direction. Well, now we have a combination of vertical and horizontal flow. And so our variables will be very similar. We no longer have D, the thickness of the aquifer. H, again, is the initial height of the water table prior to pumping. R is our radius of influence. Little r is the radius out to some point. These two variables define the shape of this potentiometric surface. It's actually the free surface in this point, the water table. And then again, the radius of the well and the height of water at the well. So now we are going to apply the Dupuy assumptions. The hydraulic gradient is dH dr, and I is constant along a vertical line. What that effectively means is, even though we have some downward vertical component, we assume these flow lines are horizontal. That's an approximation. The closer you get to the well, the worse that approximation is. And then going back to Darcy's law, Q is equal to minus KIA. We're going to do the same thing we did before. Remember that circular band around the well? Now, before, the height of that band was capital D. Well, now it's lowercase h. So if you go back to this equation right here, let's go to this one. Out to any distance r, if you take that height and then you just sweep a circular band around here, that is that's the height of that band. And so this term represents the area. And again, it's the same thing we had before, but this is an H now instead of a D. So now, how we get a solution is a little different. We're going to move the dr and the r term to the left side, but over here we have H dH, and we're going to take the integral of that. And after processing that integral and then solving for Q, we end up with this expression. So before we had 2 pi kd and h minus hw. Well, now we have pi k h squared minus hw squared. Again, we're using the radius of the well and the height of water in the well, and then the radius of influence and the initial water type as our two boundary conditions. And so this is the equation for the flow rate to a well in an unconfined aquifer as a function of these boundary conditions. And again, you can use other kinds of boundary conditions. So if you solve it in terms of, if your other boundary condition is H and R, and then instead of using the height of water at the well and the radius of the well, if you just use any R and H and then capital H and capital R for your other variable, you get this expression, and you can solve that for H. So now this is our equation that defines the height of the water table as a function of the radial distance away from the center of the well. Okay? And these equations actually give the correct flow rate, but the line of seepage is wrong because of the Dupuy assumptions. We'll look at that in the next slide or two. You can solve these equations for K. And again, use up the results of a pumping test. If you measure the height of water in the well after it comes to equilibrium and you know the radius of the well, given the radius of influence and initial water table height, you can solve for the hydraulic conductivity of your unconfined aquifer. And again, if you're using multiple observation wells, you can plug them in. Same thing we did before. And again, this is a really common way to find the hydraulic conductivity of an unconfined aquifer. You go out and you do a pump test, you let it come to equilibrium at a given pumping rate, and then you use this equation to back calculate the hydraulic conductivity. Now, because of the Dupuy assumptions, we're assuming that this is the shape of the water table. It ends up right exactly at the height of the water in the well. In reality, it ends up, the free surface comes into the well screen above that. And so if you go out to a distance of 1.5 h, where h is the initial height, those two kind of merge together. So that's kind of the difference here in the shape. It's not a big deal. In 1955, someone named Hall came up with this correction factor that shows you what is the distance. So the correction factor is this distance a here, and so here's an example. If the initial if h prime equals 50, we'll talk in a second. Well, let's see, it's written right here, is the height of the drawdown surface at r is equal to 500 times the radius of the well. The height of water at the well is 30 feet, radius of the well a half a foot, 6 inches, then we're talking just under 2 feet. So it's not a big deal. It's pretty accurate. Most of the time you wouldn't bother worrying about that, but that is a correction you can apply. Now, where this gets really useful, once again, is when we have multiple wells and we apply superposition. We can sum the contributions of individual wells the same way we did before. If we want to find the head at any point in the aquifer as a result of pumping multiple wells, we can apply the principle of superposition, but in this case, we apply the principle of superposition to the term h squared, capital H squared minus h squared, rather than to the drawdown. This is because of the governing equation. Flow is linearly proportional to h squared because of the Dupuy assumptions. And so this is the combined equation we use. If you solve this for h, we get h equals square root h squared minus 1 over pi k, the sum of qi ln capital R over Ri. So again, you could overlay a grid over your aquifer in plan view, and if you calculate for each well the radius r sub I from that well to the point in question, plug in the pumping rate for that well, repeat that for the other wells and add that up, then you can calculate the head at any point as a result of pumping from multiple wells. And this is the equation that we're going to use for our construction dewatering exercise. Incredibly useful equation, allows you to build basically a model of an analytical model of the simulating the groundwater flow inside an area, an unconfined aquifer. It's uniform. We assume it's single hydraulic conductivity, doesn't vary, the bottom is flat, those kinds of assumptions. But with those assumptions and estimating a K, we can calculate the head. Now, what if you have a partially penetrating well that doesn't go all the way to the bottom of the aquifer, which is actually quite common? At some point, you abandon these analytical equations and you run a groundwater model like ModFlow. Give you the most accurate solution, but there actually is an equation to handle this case. It gets a little complicated, but this is the flow rate up top, and if you want to get a relationship or an equation for the head as a function of R, if R over H is greater than 1.5, then it's the same equation, the same as the fully penetrating equation. So if if your radius is greater than 1.5, this initial height H, then you can just use the other equation. If less than that, then you can use this equation to solve for H. It looks pretty simple, right? Except there's this P term here, and that P term is it's kind of complicated. You know, you can plug this into a spreadsheet or Python code, and it's not too bad, but that's an equation for partial penetration, which you can use. And then, what if you have a confined aquifer that starts out confined, but you pump it so much that it becomes unconfined? So now you've got a combination of a confined and an unconfined aquifer. Well, there's an analytical solution to that as well. This is Q, and this is H, and so you know you can use that as well. Well, if you go out and look through the literature, there's actually a lot of different well equations out there. These are the main ones that I've seen that we use. And again, if it gets too complicated, you go to a full-blown numerical groundwater model like ModFlow. But well equations are very simple overall and very powerful.